IMO 2021 problem number 5, International Mathematical Olympiad. So let's see, the problem is the following from combinatorics lesson or topic 2. Squirrels Bushy and Jumpy have collected 2021 walnuts for the winter. Jumpy numbers the walnuts from 1 through 2021 and digs 2021 little holes in a circular pattern in the ground around their favorite tree. The next morning, Jumpy notices that Bushy had placed one walnut into each hole but had paid no attention to the numbering. Unhappy, Jumpy decides to reorder the walnuts by performing a sequence of 2021 moves. In the kth move, Jumpy swaps the positions of the two walnuts adjacent to walnut k. Prove that there exists a value of k such that on the kth move, Jumpy swaps some walnuts a and b such that a is less than k less than b. So for solving problems like this, for example, here we don't have n, we have 2021. So we can consider n equals 2021, and again we want to use the most useful idea. What was the idea? Considering a small example of n and finding the idea is needed. So let's check, for example, when n equals 3, because at least n must be 3 to have some meaning, because if we consider n equals 2, first element doesn't have two adjacent elements. So we start from n3 and we see without loss of generality we can consider that the numbers are like this: 1, 2, 3. We select 1 and we change 2 and 3. Then if we choose 2, 2 is greater than 1, less than 3, and we prove the problem is true when n equals 3. Now, we want to consider when n equals 4. We know that if 1 and 2 are adjacent, then after choosing 1, then by choosing 2, 1 and some numbers greater than 2 would change like this. Look, if for example we have 1, 2, x and y, and if we say, okay, after selecting 1, we will see this. And then here, we know that x is 3 or 4, so 2 is less than that, greater than 1. So in this case, if 1 and 2 are adjacent numbers, then we can say when we want to choose 2, 2 is between the two numbers that are adjacent with 2. So then the problem is true in this case. Now we want to consider the case that 1 and 2 are not adjacent, so 3 and 4 like this, and we want to check this case. So after this, we have, when we select 1, 3, 4, we change 4, 3, we change to 3, 4, then we select 2, and 4 and 3 again to change to 3, 4. Let me select here 3, 4, change to 4, 3, and then until here we didn't select any desired element. That is, for example, 2 is not between these two numbers, is less than these two numbers. And here when we select 3, 1 and 2 would change, 3 is greater than 1 and 2. After that, when we select 4, then here 2 and 1 would change, and we will see that the problem is not true for n when equals 4. So we can guess that the problem is not true when n is an even number. So we need to pay attention to parity of n. And as you can see, if we color like checkerboard scheme, alternatively we consider circles and squares, then we can see if we place small numbers in squares and large numbers on, for example here 1 and 2 in squares and 3 and 4 in squares, then by selecting each square, numbers in squares still remains in squares. So when you select a number when you select a number from circles, then the numbers in squares are greater than the number in this circle, and when we select a square, the number in that is greater than the number in the circles. So when we select, for example, 1, 3, and 4 would change. When we select 2, 3, and 4 would change. Both of them are greater than 1 and 2. When we select 3, 1 and 2 would change. And 1 and 2 are less than 3. When we select 4, 1 and 2 would change. And both of them are less than 4. So we guess that the sentence of the problem is not true for even n. So we want to just analyze the problem, not only the solution. We want to consider the ways that help us to reach the solution. So like when n equals 4, maybe the problem was find the sentence of the problem that is true for which n. Then we should consider all n, and we should find that n, when n is an even number, then the sentence is not true. And if we consider like when n equals 4, we consider alternatively like checkerboard scheme, we color, for example, circle, square, circle, square, circle, square to the end, and since we have even number, the last one won't have any problem. It would be square 2k, and it would be a circle. And now in circles we place the k minimum elements 1 to k, and from k plus 1 to k 2k, k large numbers, we place them in squares. Now when we select a square, a circle, like this, like this, like this, we would switch to square numbers, and we know that always 1 to k in each step, always 1 to k are in circles, and k plus 1 to 2k are in squares. So when we select a circle, it would be less than the two adjacent numbers, and when we select a square, for example k plus 1, we would choose two uh, less numbers than the square numbers. So we proved that the sentence of the problem is not true when n is an even number. So we would understand that parity is important. Now we need only consider odd numbers to find the ideal. When we consider n equals 5, like the thing that we said before, we can say 1 and 2. If 1 and 2 are adjacent, then the problem is true, because for example, if 2 is here, after selecting 1, 2 would go here, and then by selecting 2, 1 and other number greater than 2, and 2 is a desired element, and the sentence would be true. So we need to consider when the case that 2 is not adjacent to 1, so 2 can be here or here. Without loss of generality, we can consider 2 is here. Now we want to consider 3. If 3 is here, then after 1 select that, it would go here, then 3 would go here by selecting 2, and then 3 would be a desired element if 3 is here. If 3 is here, 3 would change here, would go here, and then by selecting 2, 3 also remains here, and then 1 and some number greater than 3, 3 again is a desired element. So let's consider the only case that is needed to prove when 3 is here. So after selecting 1, 3 won't change. After selecting 2, 3 would go here. Then by selecting 3, 1 and 2 would change. But after that, 4 is here or here. So when we select 4, 5 and some number less than 4 would change, and then in this case when 3 is here, 4 would be a desired element, and the sentence is true. Now we want to consider some cases, for example like here, 1, 2, 3, 4, 5. We want to consider some orders, 1, 2, 3, 4, 5, and we want to consider the comparing signs. So let's find the desired element. The desired elements are the things that we want to find. That, for example, here 2 is greater than this, less than this. So in this order, 2 is good, is a desired element. 3 and 4, we have 3 desired elements. Here only 4 is desired, and in this case only 3. So in all these 3 cases we would see that the number of desired elements is odd. So we define D as AI when AI is greater than AI minus 1, less than AI plus 1, or less than AI minus 1, greater than AI plus 1. And it is true we consider in general. For example, when A1 is 1, when I is 1, we consider these are only the two adjacent numbers. It means that AI is between them. So in this case, AI minus 1 is AN. So A1 between AN, A2, or greater than AN, A2. Let me correct it. Less than AN, greater than A2. And in this case, AN is between AN minus 1, A1, AN minus 1, A1, greater, less than. So we consider AI that has these properties when we call them desired elements. In this case, for example, we have 3 desired elements. Now, if we prove that in each step, if we don't choose a desired element, at least there is one desired element that has not been selected, then the sentence would be proved. Because if we select a desired element, then the problem would be true. If we don't choose a desired element, at least there is one desired element that has not been selected. So if we select the last element, 20, 21, for example, in the case of the problem, then we can say if we don't choose a desired element until 2, 20, 21, then there exists at least one desired element that has not been selected, and that would be a contradiction. So then we can prove that at least in one step we choose a desired element. So let's at first consider this claim. We want to prove the number of desired elements at first is odd. So suppose that, for example, this is less than the two adjacent numbers. So until some place it is less than, then it is greater than y. So it is greater than, maybe we have only one greater than, but we consider some greater than until we reach some less than. So x1 is less than the two adjacent numbers, then we reach after that the first element that is not desired is some numbers that is greater than the adjacent numbers. Then if we consider some desired numbers, maybe we have no desired elements. For example, look, y1 here, and then x2. It won't change. We consider only some desired, maybe 0, that we reach another x2 is less than the two numbers y2. Since we have x1, y1, x2, y2, and the last number is yk, so we have 2k elements, kxi and kyi, that they are not desired. So the number of desired elements is n minus 2k, and n is odd, 2k is even, odd minus even is odd. So we proved that the number of d is odd at first. Now we have another claim in each step. We want to prove if we don't choose a desired element, then the number of desired elements that have not been selected is odd. We define another things, number of desired elements. Number of desired elements is n of d. But now we want to define another terminology, desired elements that have not been selected yet. We consider them d1 and number of them n of d1. Now, we want to prove that if we don't choose a desired element, always n of d1 is odd. Before that, we consider a lemma. If we change the comparing sign between two elements like x and y, it changes the d, the number of desired elements, by plus or minus 2 or 0. So we want to prove it. We consider if we change this sign, for example, it has effect on x and y. So at first we consider x. We say if x is less than z, like this, then we x is less than z. So if we change this sign, then it would change to this, less than less. X was not a desired element, but now x is a desired element. So here in this case x was in this case sorry, x was greater than z. So when we change this sign, so x was a desired element, now x is not a desired element, so the number of d would decrease by 1. And in this case, if x is less than z, so let's consider this case, now x is a desired element. If we switch this sign, then we switch this sign, now it would be like this. Here x was not a desired element, now here x is a desired element, so the number of d would increase by 1. So if we can similarly we can consider y, and the number of d would change by 1. For x it would be plus or minus 1, and for y again it would be plus or minus 1. So the number of d in all would change plus 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 to minus 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 to plus minus, or minus plus would be 0. So the number of elements in d won't change or would change by 2, plus 2 or minus 2. So the number of d, the parity of d won't change because it can change only by 2. Now, by this lemma, we want to prove this claim that n of d1 is also always odd if we don't choose a desired element. So we want to prove proof of the claim. Case 1. Consider the case that AI we said that if we choose elements like this, here we want to choose element that is not a desired element. We want to say the n of d1 is again odd. So case 1, AI is less than this, less than this. Now we switch AI minus 1 and AI plus 1. So let's consider the cases. So in case 1, 1, look, we want to consider these two signs. It would be less than, greater than, less than, greater than. So we need to only consider three cases. Less than, greater than is similar to greater than, less than. So we need to only consider three cases. So case 1, 1 is the case that less than, So let's consider this case. In this case, we would see that AI minus 1, AI minus 2, all these four elements are greater than AI. So they have not been selected yet. So if we change each of them, by lemma 1, we can say it would be for this case because both of them have effect on n of d1. Changing this by lemma 1 would cause n of d1 plus or minus 2 or 0, and also this case plus or minus 2 or 0. So parity of n of d1 won't change. Now we want to consider the case that greater than, case 1, 2, if both of them are greater than. And now we want to consider these signs. If selected signs, these signs change without loss of generality, let's consider at first this sign changes. Okay, so here, and also we switch AI by switching AI minus 1 and AI plus 1. If this sign change, then we can say, okay, AI plus 1 is less than AI minus 2. From this case, AI minus 1 is less than AI minus 1. Then we know that also AI plus 2 is less than AI plus 1, and we prove that AI plus 1 is less than AI minus 1. So we can say that in this case, we proved that AI plus 2 is less than AI minus 1. So let's consider this. So we can say that if we consider the case that this sign change, then we can prove like this that this sign won't change. And now we prove that exactly one of the signs would change. And what was the sign? This sign. And now let's consider the case. Here we proved that, let's consider in the next page, we proved that this is exactly the shape of this page. And in this case, we said that only this sign changed. And if you pay attention, you would understand that AI minus 2 is greater than this, greater than this. And since now is the case that we've selected AI, so we can say that AI minus 1 and AI plus 1 have not been selected yet. So by lemma, we can say both of them have effect on n of d1. So n of d1 would change by 2 or won't change. And again, we proved that n of d1 parity doesn't change. Now, let's consider the case 1, 3, that it is less than, it is greater than. So, we call this one S1 and S2. So, in this case, we switch AI minus 1 and AI plus 1 like this. So, here, we consider the case, we call this one S1, we call this one S2. We consider the cases of changing S1 and S2. We have 4 cases. Change, doesn't change, doesn't change, doesn't change, changes, and changes, doesn't change. So we need to consider case 131 to 134. The first case, S1 changes and S2 changes. Both of them change. Now, we consider this, it would be greater than would be changed to less than, and less than would change to greater than. And let's consider the order of these numbers. We can say, okay, AI is less than AI minus 1, AI minus 1 is less than AI minus 2, AI minus 2 is less than AI plus 1, and also we can say AI minus 1 is less than AI plus 2. So all these 4 elements are greater than AI, so they have not been selected yet, these 4 elements. So changing each sign by lemma 1, all these 4 elements have effect on n of d1. So by lemma 1, by our lemma, we can say n of d1 would change for s1, changing s1 plus or minus 2 or 0 plus or minus 2 or 0. So n of d1 parity won't change. Now let's consider case 132 when none of them change. So here we have s1 like this as we had here, and S1 doesn't change, S2 doesn't change. So let's consider this case. So since nothing changed, so we can say n of d1 has not changed, because when we have n of d1 would change when one sign, at least one sign changed. And also we've seen that AI was not also a desired element. So let's consider third case, S1 changes, S2 doesn't change. So S1 changes, S2 doesn't change. And now let's consider again the orders. AI is less than AI minus 1, less than AI minus 2 by this. And AI is less than, let's consider this case. We know AI also is less than AI plus 1. So we can say that AI plus 1 and AI minus 2, both of them, AI minus 2 and AI plus 1, both of them are greater than AI, so have not been selected yet. So by changing S1, if we change S1, then we would see that n of d1, it would be, for considering this case, by changing this, we have 2 effects on them. So n of d1, since both of them have effect on n of d1, so n of d1 by lemma would change to plus, would change by 2 or won't change. So again, we proved that n of d1 parity is constant. Now let's consider the last case, case 134. S1 doesn't change and S2 changes. So if we change this one, if we don't change this one, let's consider the orders. AI is less than AI minus 1, AI minus 1, and also AI is less than AI plus 2 by this case. And the only sign that has changed was S2, so we want to consider these two elements. AI minus 1 and AI plus 2, both of them are greater than AI, so we can say both of them have not been selected yet. So by changing S2, by lemma that we proved n of d1 would change by 2 or 0. So again, we proved that the parity of n of d1 wouldn't change. Now, we want to consider case 2, that in this case AI is greater than AI minus 1 and AI plus 1. Again, we want to consider these two signs, greater than, less than, and greater than, less than. So we need to consider three cases. In case 1, greater than, and we would see that these four elements, all of them are less than AI, so they have already been selected, so changing these signs won't have any effect on n of d1 because they have been selected before, and n of d1 only consider the elements that has not been selected yet and have a special order. In case 2, we consider that is less than. Now, we want to consider if one of them at least changed, S1 or S2. Let's consider if none of them changed, so we can say no signs have been changed, so we can say that n of d1 won't change. But in this case, if, for example, consider one of them, at least one of them changed. So suppose that S1 changed like this. And after that, we can say, okay, AI minus 2 is less than AI plus 1 because S1 has been changed. And AI minus 2, we know that it is less than AI because AI minus 2 is less than AI plus 1. AI plus 1 is less than AI, so AI minus 2 is less than AI. So AI minus 2 has been selected. And n of d1 won't change by changing S1 because both of them have been selected. So we can say changing this sign wouldn't have any effect on n of d1. Similarly, we can say it is true for S2, so n of d1 won't change by changing these signs. Now, let's consider case 2, 3, that one of them is less than, another one is greater than. For example, this one is greater than this one is less than this. Now, we consider this S1 and S2. We can say AI minus 2 and AI minus 1 are less than AI, so changing S1, because they have been selected before, they have already been selected, so we can say changing S1 won't have any effect on n of d1. Now, let's consider changing S2. If S2 changed, then let's see this case, then it would change to this. Now, in this case, we can say AI plus 2 would be less than AI minus 1 would be less than AI. So we can say AI plus 2 and also AI minus 1 have been selected before, and since AI also AI, this is AI minus 1. AI minus 1 has been selected. It means by these two sentences, these two elements have been selected before AI, and we can prove that by changing S2, n of d1 won't change. And we proved that n of d1, if we don't select a desired element, then n of d1 would be odd, and if we continue like this, at last, when we select 2021, if we want to prove by contradiction, if we don't choose any desired element, but by our claim, we can say after selecting this, n of d1 is odd, and we know that after selecting this, we have selected all elements, and n of d1 should be 0, and that would be a contradiction. So in at least one step, we should choose a desired element, and we prove the problem.